So today I'm going to illustrate a difference between natural philosophy and mathematical formalism. So this is a massive topic. This is a huge sort of discussion topic, academic area. And I'm going to use as a starting point another video I did talking about the derivation of the canonical ensemble, which is a thermodynamic quantity. And we're gonna use that as a jumping off point, as an example, to discuss the difference between these two. So what do I mean by natural philosophy? What I mean is, if you remember, for our canonical ensemble, if we take, for example, a one particle system, we know that we can say that the partial differential of the probability, let me make sure I get this right, with respect to position, it times the partial differential of the energy with respect to momentum minus the partial differential of the probability with respect to momentum times the partial differential with respect to energy is 0. Okay, so this came out in our derivation of the canonical ensemble, and the point is that this was based on the laws of physics. So what led us to this? Well, there was a few things. One, we knew that P1, which is the force, F1, is equal negative the partial derivative of the energy function with respect to position. Okay, we knew the speed, x1 dot, which is the speed of the particle, is the partial derivative of the energy function with respect to momentum. And we also had these other definitions for, well, we know that dx1 is equal to x1 dot dt, and dp1 is equal to p1 dot dt. Interesting to note that these may not necessarily be true in the quantum mechanical sense. So this is actually classical mechanics. Okay, so this all led us to a probability function that had the form a times e to the negative b times epsilon. So the point that I want to demonstrate here today is that, let me see if I can pull this down, get this all on the sort of the same screen. Let's try that again. So what I've sort of demonstrated on the left here is sort of a natural philosophy, a natural philosophical argument to arrive at this equation. Okay. What I want to show you as well is that from a pure mathematics standpoint, anyone who's familiar with differential equations will also know that if you take the second, let's use orange, second order derivative of p and subtract the root of b times the probability again equals 0. Now this equation will also yield, in general it actually yields an additional term, but it is definitely true that you get this form, and we're gonna just quickly do these derivatives to show that it's true. So let's do that. If you take p dot, which is the first, I shouldn't call it p dot. Let's clarify something here. In this sense, I'm using p dot. I'm defining it as the derivative of p with respect to e. Sorry, that's very unconventional. It's just how I wrote this here. So if we take the first derivative, you're going to get negative b a e to the negative b epsilon. Okay. And then I guess I sort of did this a little bit incorrectly here. This is supposed to be root b, or actually no, this is supposed to be b squared, and this will just be b. Sorry, let's try that again. So p dot is going to equal negative b a e to the negative b epsilon. and then P double dot. You take it down again, the negative and the negative become a plus. You get B squared A e to the negative BE. But of course, you realize that this is just how we define P in the first place. So P dot equals B squared times P, which is the same as this first equation we wrote. So the point that I'm illustrating is that when you compare these two differential equations, we can call this 1 and this is 2, where 2 is the mathematical formalism that's true, and 1 is a natural philosophical argument that's true. It begs the question, are both true? And I'm going to illustrate how, first of all, they're not, and that natural philosophy and what some might call theoretical physics, theoretical physics it differs from mathematical formalism. Okay, so let's assume they're true. If you assume 1 and 2 are true. Okay, if they are true, then you could make a reasonable assumption that, for example, this term and this term could be equal. Okay, so if you have the partial dp by the momentum of the particle and then partial d epsilon by the position of the particle, we're going to assert that it's equal to b squared times p. Okay, so let's just do this math, and I'm going to illustrate that this is an absurd statement. Okay, so for a single particle, our energy function can be something as simple as a1 p1 squared plus b1x. All right, so let's slot that in, and let's take and p of course is here. All right, so this is p. So we take the partial. First thing we should do actually is rewrite p in terms of p1 and x. So p is going to be equal to a to the times e to the negative b a1 p1 squared e to the negative b b1x. So if we take, let's do this one first. If you take the partial of p with respect to p1, you're going to get a, the e negative b b1x doesn't get touched. The other term has a negative 2 p1 b a1 in front, and then you get the same term back, a1 p1 squared, and then this term is simply b1. Okay, the partial of e with respect to x1 is just b1, and we're asserting that this is equal to b squared p. Now what's p? P is a e to the negative b. We're going to write it in this way: e negative b a1 p1 squared e negative b b1x. Now to assert that both of these statements are true, and I'm just going to copy this down. Okay, we don't need that. So we're trying to assert that both of these things are true, and the argument was that both differential equations produce the same probability function. And let's just continue down this line of reasoning. Well, of course, our a cancels. A cancels. E to the negative b1 bx cancels. This cancels. This cancels. 1b cancels. Okay, so we can see that. Let's use a different color. So this b cancels, and then that one goes away. And what we are left with is negative 2 p1 a1 equals b. Okay, so physically, b has a meaning, and it's 1 over kt. So let's put that in. We get p1 a1 equals 1 over kt. Well, you're probably already realizing something has gone horribly wrong, because t is going to be equal to negative 1 over 2 p1 a1 k, where k is the Boltzmann constant, kb. Okay, so we're saying temperature is negative. Physically, this result, it cannot be true. Okay, so this is absurd. This is an absurd um, assertion to make. What well, we know that momentum can be, is positive. General, a 1 over 2m positive, k is positive. Momentum could be negative, and that would make things fine. But if this asserts that if momentum is positive, then if momentum is positive, then t is negative, and this is really what's absurd. Okay, so what I'm demonstrating here is that obviously, if we go way back up here, we asserted this is true, and I'm going to say this is not true in general for the probability density function of a system, of a simple Newtonian system. So obviously you can see that there's a difference here between the natural philosophical argument and the mathematical formalism, which yields the same probability function. So I just wanted to give an example on that. I think this is something, it's an interesting facet of theoretical physics, and to somebody arguing about the logic of physics, or the logic of theoretical physics versus other types of philosophy and logic, I think this is a strong argument in favor of natural philosophy as a way of explaining reality.